Chi-square tests for goodness of fit. The significance tests that have been discussed thus far consist of 1 and 2 sample Z and T tests. These have been extremely helpful with many different types of problems. However, these tests are used for continuous data to determine whether the sample parameter differs significantly from a known population parameter. For example, a one-sample Z-test might be used to test whether the mean height of a sample of students is significantly different from the population mean height of all students. In this case, the difference between the sample mean and the population mean is measured in units of the standard error. What if categorical or count data is given and the goal is to determine whether the entirety of observed data differs significantly from the entirety of expected data under a particular hypothesis? For example, instead of wanting to know if the mean height of a sample of students is different from the population mean height, maybe the desired outcome is knowing if the heights of students in a school are evenly distributed across the categories of short, medium, and tall. None of the tests that have been learned thus far can work with this type of situation. This is where chi-squared tests are used. Chi-squared tests are used for categorical or count data and test whether the observed data differ significantly from the expected data. Chi, the CHI, is pronounced chi and comes from the Greek symbol chi. The symbol for chi-squared is that Greek letter chi raised to the second power, or squared. As with all significance tests, we will need to first check conditions, second write hypotheses, third find chi-squared, fourth find the p-value, and the fifth and final step is to interpret and draw conclusions. The following conditions must be satisfied to perform a chi-squared test. First, it has to be random. The data must come from a well-designed simple random sample, or SRS. Number 2 is 10%. When sampling without replacement, our sample size must be less than or equal to the population, capital N, divided by 10. And third, the law of large counts. All expected counts are greater than or equal to 5. Now let's talk about the chi-squared hypotheses. When performing a chi-squared test for goodness of fit, one is checking to see if a sample has a specific distribution in the population of interest. That means hypotheses will be constructed as follows. For the null hypothesis, the sample distribution is the same as the population distribution, meaning there is no significant difference between the observed and expected values. Therefore, no association between the variable and population occurs, because any differences are by chance. In short, the observed value is equal to the expected value. And for the alternative hypothesis, the sample distribution differs from the population because there are significant differences between the observed and expected values due to association and not by chance. In short, the observed value is not equal to the expected value. The chi-squared statistic measures the distance between observed counts and expected counts using the formula chi-squared is equal to the sum of the observed value minus the expected value, quantity squared, divided by the expected value, where capital O with I in subscript is the observed value or count for each category I, and capital E with I in subscript is the expected value or count for each category I. The expected counts, or capital E in our formula, can be found by multiplying the sample size by the proportion in each category. Just as with t-tests, the chi-squared value can be used to find the p-value. The chi-squared distribution table can be used to determine between what significance level the chi-squared value lands. It also uses its own set of degrees of freedom that come from subtracting the number of categories by 1. In other words, it's k minus 1, where k is the number of categories in the test. Let's say the goal is to determine if there is an association between the 5 flavors of ice cream at a store and the sales of each flavor. Data is collected on the ice cream flavors purchased by a sample of 100 individuals. The null hypothesis is that the ice cream flavor does not affect the sales and that each flavor sells equally. A chi-squared test is performed, which calculates that chi-squared is equal to 9 and 35/100ths. The degrees of freedom would be 5 minus 1, which is equal to 4, because there are 5 categories or 5 flavors of ice cream. Using a chi-squared distribution table such as the one shown below, one can determine where chi-squared, which is equal to 9 and 35/100ths, with the degrees of freedom of 4, lies between. So we have 9 and 35/100ths, and the degrees of freedom are 4. I'm looking for a value between two values that are outside of 9 and 35/100ths, so that will end up being the significance level between 5/100ths and 1/10. This means that the desired p-value will also lie between these two values. If the test asks for an alpha value that is equal to 5/100ths, the p-value would be greater and therefore the null hypothesis would fail to be rejected. There wouldn't be convincing evidence that each flavor of ice cream sells equally. If the test asks for an alpha value of 1/10, the p-value would be less and the null hypothesis would then be rejected. Technology can also be used to calculate a precise value for p. There are online chi-squared calculators as well as commands on handhelds such as a TI-89. The command in a handheld typically holds the form of chi-squared and then CDF and then the variables a, b, and c in parentheses, where a represents the chi-squared value, b represents a very large number, usually 10,000 or more, and variable c represents the degrees of freedom.